Les habla Pocho Salcedo y la idea central de estos próximos minutos es la democratización del espacio interplanetario. Vamos a ver cómo una tecnología emergente posibilita que casi todos los países del mundo puedan poner sus propios satélites orbitando la Tierra y otros planetas. Damos la bienvenida a nuestra audiencia en el Cono Sur y a todos aquellos que nos acompañan de costa a costa en los Estados Unidos de Norteamérica, Hawái y Puerto Rico. Una vez más, invitándolos desde el Estudio 3 aquí en Nueva York a esta caminata que va más allá de los titulares. Bienvenidos al ADN de las noticias. Lo que parecía inimaginable es ahora realidad por el costo aproximado de menos de un 2% de la inversión de un satélite tradicional. Países, universidades, escuelas secundarias y hasta empresas privadas pueden ahora poner en órbita satélites en el espacio para una cantidad de aplicaciones. Hoy con nosotros desde San Luis Obispo, California, el doctor John Bellardo, director del laboratorio Cal Poly CubeSat. Dr. John Bellardo, welcome to the show.
Thank you. Thanks for having me.
John Michael Bellardo is professor in California Polytechnic State University and is assessor of the Cal Poly CubeSat laboratory. Professor Bellardo has been working with CubeSats for 13 years and has been involved in more than 10 spaceflight missions.
Dr. Bellardo, this is a very interesting topic, and just to start approaching this new technology to many of us, let's talk about what is the existing standard technology, the time, money, and energy that is needed to build and launch traditional satellites.
Historically, the majority of the satellites have been the size of a bus, right? So it's a very large, on the order of 5 or 10 years sometimes to design, test, develop the spacecraft. When you're working on something for so long, it ends up being very expensive. So it could be as much as, $750 million US or so to put one of those together. So they end up being very large, very time consuming, very expensive. And then because they're so large and expensive, the companies that are developing them have a very, very low risk. They don't want to take any risks or any unnecessary design decisions that would result in potentially the spacecraft not being able to perform its mission when it's on orbit. Right? So you end up in this paradigm where it's very expensive and very risk adverse. And so you end up not being able to do a lot of technology experimentations. You really basically say, golly, we know how to build these communication satellites that are very robust. So we're going to build a large communication satellite and launch it, and we know it's going to serve the purposes for internet access or for allowing communication with ships out when they're in the middle of the ocean, away from other ground-based infrastructure. Right? So that's historically how a lot of the satellites have been designed and built.
What is a CubeSat? How did the technology come about and its impact on science and the exploration of space? Why is it possible that a cube of 10 by 10 and 10 centimeters, about 4 inches, can have such an array of capabilities?
Yeah, so CubeSats were originally envisioned basically as an educational tool, right? Because these really large spacecraft were so risk adverse, they were hard to use to train students in the appropriate techniques to build a CubeSat, or to build a satellite rather. So your university experience was not very hands-on. It was more theoretical. This is what you should do when you get out and build a satellite. And even when you started at one of the space companies, you weren't necessarily allowed to, touch the flight hardware or work directly with the flight hardware from the beginning. Right? So the CubeSats were envisioned as a very rapid way to build a spacecraft, and the spacecraft itself would be inherently higher risk, but it would be a whole lot cheaper and the schedule would be a lot shorter until we could have student involvement and they could use that to learn and expand their skill set before they went out to work in some of these aerospace firms. Right, so as you mentioned, one CubeSat is 10 by 10 by 10 centimeters for illustrative purposes, I have a little cardboard model here in my office, and you can see, a 1U CubeSat does indeed fit in the size of my hand. Right? One of the key enabling technologies for CubeSats wasn't the form factor itself in the standard. It was actually in the launch capability. And so one of the early challenges was finding rockets that were willing and able to take these small satellites up to orbit as secondary payloads. So not the primary payload, the CubeSats aren't the one that's really paying for the rocket. That would be cost prohibitive from a launch standpoint. So one of the roles that Cal Poly played early on was we developed the very first deployer for CubeSats. So we called that the Poly Picosat Orbital Deployer. We abbreviated that PPOD. And it would basically fit 3 of those 1U CubeSats into a container. And there's a spring in the bottom. When the rocket got to space, it would send a deployment signal to the container. The door would open up, and the spring would push those 3 CubeSats out just like a jack-in-the-box. Right? And so they just kind of get pushed out into space. So we developed the original deployer, and we worked to secure a number of the original launches. Right? So now, the current state, NASA is facilitating a lot of the CubeSat launches, and you can get third parties as well that are more than happy to help you facilitate these launches. But early on, that opportunity just didn't exist. And so we work with a number of the launch providers in order to secure those spots to allow these educational universities and institutions to start deploying these satellites. As I said, the very first launches, a couple of launches we actually did were out of Kazakhstan over in Russia, because they were the ones that were willing to accept our deployers on, despite the fact that they're considered higher risk. And then after it was demonstrated that the deployer kept the rocket and kept the primary payload safe, we were able to move to other launch vehicles, and we've flown on most of the US-based launch vehicles at this point. So we've gone from 0 CubeSats flown 15 years ago, and now there's probably 500 or 600, maybe thousands have been flown worldwide. So it's been very successful. So the dispenser was real key to finding the launch opportunities. And once the launch opportunities were there, it wasn't just universities that were interested, right? They were definitely interested from an educational standpoint, but then you get, NASA centers like JPL, organizations like the Planetary Society interested in doing science and tech demos that were looking at this, all these launch opportunities for CubeSat-sized spacecraft, and then really taking advantage of the launch opportunities to do a lot of interesting science and tech demos.
So the CubeSat laboratory has a national and international role, sort of providing standards and best practices for the industry. Is that how the industry is coalescing around the standards and recommendations that you're making worldwide?
Yes. So early on, when there was no standard, right, we developed the PPOD, and we satellite designers built to that particular standard. And since then, as CubeSats have become more popular, Cal Poly has continued to update the standard to reflect, change in restrictions. Very early on, there were restrictions in terms of, you couldn't have pressurized gas on board the satellite, on board the CubeSat, because that would be too much of a risk to the rocket. But as the technology has matured and people become more comfortable with it, that restriction has been relaxed a little bit. And so now you see CubeSats that have, some pressurized gas to provide a little bit of propulsion, and we've updated the standard to accommodate that. So we continue to update the standard as the industry becomes more, acceptable or accepting and understanding of the CubeSats. So we definitely continue to do that, and it's used, as you mentioned, internationally by almost all organizations that build CubeSats.
I understand the CubeSats are used by academia, national and internationally, organizations, private enterprises, even countries who never had access to that technology, who never launched a satellite into space, are able to do so. In a way, this is democratizing the space exploration. What do you think is is the next step, the next development vis-a-vis CubeSats?
So I absolutely agree with you that it's democratizing access to space. We've seen a couple of different examples here, right? So the first is our role facilitating launches early on in the development of the growth of CubeSats. We saw a number of spacecraft come through and be launched that from countries that were not spacefaring nations before, and their first spacecraft that they ever launched was CubeSat form factor, and that made them a spacefaring nation because the other style of spacecraft was just too resource intensive for them to put together. On the other end of the spectrum, we've worked with a couple of different high school organizations here in the United States, one based out of Irvine in California, Southern California, and the other near Kennedy Space Center out in Florida, right? And so the educational impacts that were originally envisioned for universities and college level programs have been able to be applied to high school programs as well, which is great. In terms of developments going forward, the CubeSats, because they are so small, again, 10 by 10 centimeters, the traditional electronics that people were used to using in spacecraft just didn't fit, right? And so that forced all the developers to be more creative and look towards other non-traditional sources for their electronics and the sensors they put in the spacecraft. And as a result, you see a lot more off-the-shelf parts, things that you might find either in your car or maybe in your cell phone being used in the CubeSats because they actually fit in the low power as opposed to the other pre-existing alternatives. So one of the directions I see this going is that the form factor and the size of the CubeSats will drive, even further the miniaturization of the technologies that we use in space. And that's going to eventually flow down to other spacecraft where you can take either one of those bus-sized spacecraft that I was talking about before, and maybe use some of the more miniature technology and make it smaller. It's still going to be much larger than a CubeSat, but you might be able to do the same job, with a smaller spacecraft. Or you might be able to, for example, there's this middle range of spacecraft commonly referred to as small sats. You may have heard of, say, Starlink or OneWeb, that are building constellations of these communication satellites. They fall more in the, I want to say 200 to 300 kilogram range in terms of weight. The CubeSats here, the 1U is limited to 1 kilogram. So that gives you a rough idea about how much bigger they are. And they benefit greatly from, so they're larger, but they still benefit from the miniaturized technology because they can do a lot more in that same volume than they could have, say 10 years ago. So I see the CubeSat still being able to drive the technology development in addition to being able to do interesting science on their own and serve as a good educational tool for students in universities and other institutions.
We'll be right back, take a short pause, and we'll talk more about this extraordinary technology and what other applications exist, and looking at deep space exploration. Well, there's a lot more coming in the show. We'll be right back. Welcome back, Dr. Bellardo. I want to ask you about sat cubes that have left the Earth orbit and gone into deep space. I understand there were some of those satellites that were launched and directed to Mars. Tell us a little bit about that.
Yeah, that's absolutely true. So far, there have been two spacecraft, two CubeSats, that have left Earth orbit. They're both part of the MARCO mission. MARCO stands for Mars Cube 1. It was led by JPL, but really a partnership of a bunch of different institutions with CubeSat experience that helped work on those spacecraft. The goal of Mars Cube 1, the MARCO spacecraft, was to serve as a communication relay. So these two small CubeSats. By small, I know I showed you the 1U CubeSat earlier that was 10 by 10 by 10 centimeters. These were considered a 6U CubeSat, so basically 6 times the size of that. So approximately the size of a small briefcase when they were launched. All right, so these 2 small spacecraft launched with the InSight lander. So that was back a couple years ago. And the challenge that they were trying to address was, as InSight was going through the entry, descent, and landing phase, the EDL phase, where it very quickly deorbits and then deploys the parachute and does gentle touchdown on the Martian surface, there was no communication coverage with the lander itself, right? So the operators back at JPL in Pasadena weren't going to know whether or not the landing was successful, and they weren't going to be able to get sort of real-time data until maybe a couple hours later, when one of the other pre-existing Martian satellites flew overhead. And so the idea behind the Marco spacecraft was that they would fly by Mars and they'd time it such that they were passing past the red planet while InSight was landing. And they'd receive all the data from InSight as it was descending, and then they'd forward it or relay it back to Earth so that the engineers could have access to that data in, well, as real time as you can get with Martian communication. Right, and that was the general idea behind the 2 Marco spacecraft. The mission was a huge success. They're both the spacecraft. They sent 2 in case one had issues, but they both ended up making it to Mars. They navigated out there independently, so they're deployed near Earth, and they did their own maneuvers to get all the way to Mars, and they both ended up relaying the data back. So in that sense, it was very successful.
You were involved in at least 10 launches of these. Tell us, what was the experience from the first one to the 10th one? How did it change? You got hairier, or just how that process went?
Yeah, so anytime you launch your first satellite, there's always a lot of anxiety, right? Because this is something, even with a CubeSat, you spend a couple of years working on. And if there's an issue with the rocket, then there's a couple of years of time is not going to be going to good use. So there's always a lot of anxiety, especially for your first CubeSat, especially for your first launch. That does change a little bit over time as you experience more launches. As an instructor here, I've had the privilege to be involved in many launches, and so my anxiety level has changed over time. But that's not true of the students. When it's the student's first launch, or a company's first launch, or even engineers at JPL, or when folks from from other countries come to visit. Vandenberg is about an hour and a half away from where we are here in San Luis, so it's relatively close. So we get a lot of folks coming to watch the launches and interact with them. And it doesn't matter how old you are, what country you come from. There's a lot of anxiety during your first launch or two. So in that sense, you calm down a little bit, I guess, the more launches you go through. But there's always, it's always a very exciting time, right? You want to see the launch itself is exciting, then you're excited to operate the spacecraft when it gets in orbit to hopefully accomplish whatever the goals were that you set out to do.
What are some of the applications in for sat cubes from the point of view of the private sector?
So a lot of the private sector CubeSats, for instance, you may have heard of the company Planet Labs that provides a lot of Earth-based imagery and services around Earth-based imagery. They're using the CubeSats as a way to acquire that imagery for a couple of reasons. One, as a CubeSat is smaller and cheaper, and so they don't have to invest as much money in really big spacecraft. But also they're able to put up constellations of these spacecraft, right? So instead of being able to put up one spacecraft on a $300 million budget, now maybe you can put up 250 spacecraft on the same budget. And so then they get coverage around the Earth that's much better, and they revisit or they overfly the same spot on the planet more frequently. And so you get better performance metrics by having these constellations of spacecraft up there. So they save on the individual cost, but they also get better coverage. So a lot of the early commercial use of CubeSats leverage that. Either optical imagery like something like Planet Labs. There's a lot of CubeSats up there that are designed to monitor for radio traffic, right? So, for instance, receiving the tracking beacons that airplanes, commercial airliners use to report their position, right? So you can monitor the flow of the air traffic even when it's out in the middle of the ocean. It doesn't have, again, any ground-based coverage. Those are some examples of where we've seen a lot of the commercial applications.
What's the lifespan of a CubeSat?
So the CubeSats that we build with the commercial off-the-shelf parts, we try to make them achieve their mission within about 6 months, right? Because space is a harsher environment than down here on Earth. The parts are expected to, effectively wear out faster. We've seen, extremes where spacecraft have been up there, CubeSats have been up there and operational for 10 or 11 years, right? Which is wonderful. But as I said, that's an extreme. You're not going to get that in the average case. I'd say the CubeSats that work when they're deployed are probably operational for a couple of years, right? That's a reasonable lifetime. We're still operating the LightSail spacecraft, which was a joint mission with the Planetary Society. And that one's been operational for a couple of years, for instance.
Traffic jams in planet Earth in big cities, large cities, but I can imagine what is out there in orbit because there are satellites of all sizes, of all places in the world. How is this regulated?
Not very well, I think is the high-level summary. So right now, there's a lot of concern about space traffic management and ensuring that the satellites that are in space are not going to interfere with each other, right? So that could be, there's primarily a concern of collision. If two spacecrafts actually hit each other, it obviously damages the two spacecraft involved, but it usually creates a bunch of additional debris, right? These don't just, collide with each other and then stick together and do nothing, right? They scatter, all sorts of bits and pieces when they collide. And those small pieces, even though they don't weigh very much, are traveling, faster than bullets here on Earth, right? And so if they hit something else, they can also cause a lot of damage. So there's concern about debris created from these collisions. So there's a lot of discussion about how to better manage the situation. What's currently in place is expectations that the spacecraft re-enter the Earth's atmosphere. So basically deorbit and burn up as it's re-entering within 25 years of when its mission is done, right? So that's the current expectation. And the CubeSats that are launched here from the US are all required to meet that particular constraint. But again, there's a common feeling that 25-year requirement is not sufficient, especially given the higher volume of spacecraft that are going up now with these larger constellations with, like I said, Planet Labs and SpaceX. And if you're interested in, what maybe a traffic jam in space looks like, there's a nice video from a rocket that was launched out of India a couple of years ago that deployed like 110 different spacecraft. Right, and you can just watch the deployment video, and these things just keep coming off and off and off, and it almost looks like you can walk on the spacecraft out a ways. So if you're interested in visualizing what it might look like when it's crowded up there, you can probably find that on YouTube or somewhere.
In your generation, you were a young guy, and how did this interest for this area of technology started with you, and how do you see over a period of time, the development and the interest in your students who are more aware of this technology? They are born probably already with a cell phone or some device in their hands when they were very young. So tell us a little bit about where you came from and what you see with the young people today.
Yeah, absolutely. So my background is in computer science. I have my PhD in the area of basically networking. And the classes I teach here at Cal Poly are all computer science classes. Though I had always been interested in aerospace. It was one of the careers I considered when I was picking where to go for university. And so when I got to Cal Poly and realized that they had this CubeSat program that was relatively young, but it was also relatively unique in that there's very few universities across the entire country, let alone world, that had a similar program. I thought it was a great opportunity to take what I know about computing, right, and apply it in a different area that I was also very excited about. Right? So that's how I ended up being involved with the CubeSat program here at Cal Poly. In terms of sort of younger generation, next generation coming up, we definitely see. I talked to a lot of students who are interested in Cal Poly specifically because of the CubeSat program, so they've heard about it. They come to visit campus. They want to talk about it. They want to take a tour of the facilities in the lab. That's relatively new, right? And I'm sure it applies not just to Cal Poly, because there's a number, at this point, there's a number of other institutions across the U.S. that have a sort of a standing CubeSat program. So that part's interesting. A lot of times by the time somebody's applying to a university, they've already either been really excited by the technology and being able to use it and apply it in new ways, or they've decided that the technology isn't for them. So I don't see as much of the CubeSat, influencing, let's say, a senior in high school as much as it does, you have somebody in middle school and say, oh, a CubeSat, oh, one of my high school friends was able to build this. This is exciting. I want to get involved.
Thank you very much again.
You're very welcome, and thanks for having me on the show. I definitely enjoyed it.
Thank you. Nunca podíamos haberlo pensado 3 décadas atrás, que por medio de un teléfono portátil nos comunicaríamos a un bajísimo costo con todo el mundo. Esa es una verdadera revolución. En ese proceso se encuentra la tecnología satelital. Ahora ella es accesible a una gran parte de los países en el mundo. Uno puede construirlos, lanzarlos al espacio y diseñarlos para aplicaciones especiales, todo en un cubo de 10 centímetros o 4 pulgadas de lado. Países que nunca soñaron tener su programa espacial y tecnología satelital ahora lo tienen. El espacio se ha democratizado tanto que hasta escuelas superiores ya están construyendo sus propios satélites. Gracias por permitirnos ser parte de su día. Hasta la próxima oportunidad, cuando desde el Estudio 3 de Nueva York pongamos a su consideración otra edición del ADN de las noticias.